Today I'm with Dr. Bekir Bartin, Associate Professor of Ozayin University in Istanbul. He was the founding chair of the Civil Engineering Department at Attinbas University and a research associate at Rutgers until 2012. His research expertise lies in the development of simulation models of large-scale complex transportation systems, application of reinforcement learning methods in traffic simulation, economic evaluation of transportation investment projects, and traffic safety and security. He's also been the PI and co-PI on more than 20 research projects, including at the C2 Smart Center, where I'm happy to call him a colleague. Today's webinar is called Extracting Horizontal Alignment Information from Geographic Information System Maps, a Clustering Approach. Dr. Bartin, whenever you're ready.
Okay, thank you, John. Hi, everyone. Good afternoon. Again, my name is Bekir Bartin. The title of the presentation is Extracting Horizontal Alignment Information from GIS Maps, and the approach is a clustering approach. Now, this is a byproduct of a research project that we conducted NYU, Rutgers, and Drive Engineering conducted for New Jersey Department of Transportation back in 2018. And the outline of the presentation is as follows. First, I will give you a brief background on roadway horizontal alignment for those who are not familiar, and then talk about the available methods and challenges for extracting this information. And I will, after setting the stage, I would like to give the objectives of this presentation and present the proposed clustering approach. And I will use one roadway to validate the results of the proposed approach, then talk about briefly about the future work on this specific subject. Now, as far as the background, let's start with the terminology so that it is easier to follow the entire presentation. Now, when we are talking about horizontal alignment, so there are when we're dealing with roadways, we have the vertical alignment and also the horizontal alignment. So when if you think of it, you're just looking at the roadway from a bird's eye view. And a curve section just makes the transition between tangent sections more smoother. So when you look at this, we have the basic elements of a horizontal curvature is the start of the curve, which is the point of curvature, PC, and the end of the curve, which is the point of tangent, PT, and PI is the point where it's an imaginary point. If these tangent lines, if there was no curvature, they would have met at the PI point. And we have the middle ordinate, and the most important one is the central angle delta. Now, we have to make a distinction between a tangent section and a curve section. Now, when you say tangent section, is i.e. it is a straight section, but it also means there is no significant curvature. So we usually assume that a section is tangent if the radius is greater than a certain threshold, for instance, 12,000 feet. Now, there are different, so the one that I just showed you here is a simple curve. There are also different types of curve. For instance, the one that you see here is a compound curve where there is no tangent section combining them with two different radius values. And we have two reverse curve without a tangent section. We also have a spiral curve with a varying radius values. Now, let's talk about the background. Why are we interested in horizontal alignment data? Now, this information is crucial and necessary because, for instance, in the United States, a quarter of the crashes occur on curved sections. So in order to put countermeasures, for instance, flashing beacons or rumble strips or warning signs, curvature warning signs, we need to know exactly where the curves are. And you might think that this information is easy to come by, but on the contrary, the data set is rarely available in a usable format, like in a database, not in a database that one can easily download and use for different safety purposes. Now, for instance, the most reliable way of reaching a curvature data is through as-built plans. You can go to the archives for a given roadway and then look at a given section. And then, for instance, in this case, you see a specific curve with a PC, start of the curve, PT, the end of the curve, and the radius value. This all looks nice. But when you are depending on your scope, if you're dealing with a network-wide analysis, obviously going through all the plan sheets is not feasible. It is time-consuming, it is costly, and also not all the plan sheets are as nice looking as these ones. If you go to the old archives, you can see plan sheets like this, very hard to decipher and get the information that you need. Now, the necessity of this data sets and the difficulties in obtaining them have become more apparent in recent years, especially since the publication of the first edition of Highway Safety Manual, which has become a U.S. national standard for safety analysis, which includes a lot of predictive formulas for estimating the number of crashes, the impact of certain safety countermeasures. Many state agencies, they would like to use it, but it requires abundant number of data, a lot of data in a certain format. So they have been trying to modify their existing databases to comply with the requirements of the Highway Safety Manual, HSM for short. Now that we set the stage and talked about the hardships of getting horizontal alignment data, let's talk about what are the available methods and what are the challenges for each method. Now, the available methods, obviously we talked about the as-built plan sheets. The second one is the field survey. You might have seen one of these guys on the roadway with their tripod and the total station, and another guy with a measuring rod giving reference points. Obviously, this is the most reliable, but it will take a long time to extract a horizontal alignment data of a given roadway, and it is time consuming, it is costly. The second one is the survey vehicles. There are vehicles that many consulting companies and also DOTs use to extract horizontal alignment data, which is equipped with global positioning systems, cameras, LiDAR detectors, and other measuring devices. Again, you have to drive on the roadway to cover most of the network, and you have to drive steadily. You cannot go zigzag and change lanes for reliability reasons. The other one is manual extraction. So this is one of the methods that has been widely used by many researchers because it is quite, I wouldn't say easy, but it is way better than the other methods, the field surveys and the survey, because it's faster. So you can look at a given roadway, and by visual inspection, you can find out where the PC is, where the PT is, and then use a method called the Chord Method, which is usually done on the field. Is a quick and dirty way of finding the radius. What you do is you find the distance, the direct distance of the chord between the PC and the PT, and then find the middle ordinate, which is M, and then it gives you a reliable way of calculating the radius of the circle. However, going through the if you have 5, 10, maybe 100 roadways, each of them at least 10 miles long, that requires a lot of manpower. You have to go through the aerial imagery one by one and do this. And also it is very biased, it is prone to errors. So you have to, so it's kind of a visual inspection. So for one person, the PC might be here. For another person, the PC could be right here. So there is not a definite answer. So, and even slight differences between the PC location and the PT location can change the value of the radius. As a matter of fact, as part of the research project that we conducted, we it was, I believe, Highway 347 in South Jersey. It's about 8 miles long. We gave that task, this task, to 15 different people, 15 different PhD students and master students, and the number of curves that were identified varied between, I believe, 10 to 27, with an average of 17 curves. So, you know, from one person to another, because there's a human, it's subjective, let me put it that way. So it is prone to errors. The other methods are automated image processing. And also the last one, last but not the least, is the GIS, Geographic Information System, Roadway centerline shapefiles. Now, what are the challenges? As I said, they all have their pros and cons. For large-scale road networks, there are two methods that are more viable. One is survey vehicles, but as I said before, it's expensive, it is costly, and it requires a lot of post-processing, data post-processing. And the second one is the one that we use in this presentation, is the GIS maps. Now, the good thing about the GIS maps is it is available for nearly all the roadways. I mean, you can find the GIS maps of local roadways, local streets. But there are very few available tools to process that data. So it is there. It has been done. So the way the GIS maps are formed is you take an orthophoto or a high resolution satellite image, and there are companies who process these images and put vertices on the center line of the roadway. So gradually you have the entire GIS map of the highways of a given country. And this data set is available on many different platforms. If you go to the New Jersey Department of Transportation website, you can download all the detailed GIS maps. Now, the data is there, but how do we process that? The available GIS-based tools to extract the horizontal alignment data, there are 4 of them: the curve calculator and curve extension. It is available. It's related to ArcMap toolbars. It's a part of the toolbar of ArcMap, but it requires manual identification of curves. There is one curve finder, but it's not publicly available. And the last one is ROCA, Roadway Curvature Analysis, I believe. It's by Czech researchers from Czech Republic. It can do network-wide analysis. It doesn't require any manual input, but it requires training data. It uses a naive Bayes classifier, but it requires, as I said, an extensive training data to run the model, the tool. Now, what are the objectives after setting the stage? So obviously there's a need for a computer tool that uses the GIS roadway maps, extracts the horizontal alignment data quickly and accurately, and it should be able to do it network-wide, and it should be accessible to researchers, to public. Now, the objective of this talk is I would like to present a reliable and efficient method that we developed for extracting roadway alignment data from GIS centerline maps, and to present the validation of this approach using a roadway from the United States. So let's talk about the proposed approach. I would like to first give you the formulation. The idea is simple. It is centered on the idea that the distinct roadway sections, either curved or tangent, they have the same curvature values. So as I said before, a roadway is represented by discrete vertices in GIS maps. If you look at this hypothetical roadway, we know the way you see on the GIS map is just a polyline, but you can extract the vertices that were used to create those polylines. So this is actually placed manually by someone. So you can extract those. You can extract also the X and Y coordinates of each vertex using the forward finite differences. You can calculate the heading angle. So the tangent of the heading angle it can be easily calculated, and the tangent of the heading angle gives you the approximated derivative of that point. You can also find out the second order derivative approximation, and using the first order derivative and the second order derivative, you can find out the curvature value using. So this is obviously an approximation. So if you look at this roadway section, which I created in Google Earth, obviously it's a hypothetical roadway section. There are 3 tangent sections, section 1, section 3, and section 5. And there are 3 curve sections, section 2, section 4, and section 6. If I remember correctly, there are a total of 78 vertices that make up this roadway. So by extracting the vertices, and I know the X and Y coordinates, using the approximation method, I can approximate the curvature of each vertex. And when I plot this on a scatter plot on the right, you can see clearly that the tangent sections have nearly 0 curvature values, and the curved sections have distinctly different from 0 curvature values. So when you look at this, obviously this is a very obvious example. You can easily see that this is a curved section, this is a curved section, and this is a curved section, and these are tangent sections. So the observation is this: the curvatures of vertices within distant sections are clusters. The curvature values of the vertices within the distinct sections, either curved or tangent, they're clustered closely. So we can use these values to detect the horizontal curves or tangents. The intuition is this. This looks exactly to the generic clustering algorithm, which is based on the minimum within group distance criteria. So going back to the previous scatter plot, I can, if I use any generic clustering method, I can find that this is one cluster, this is one cluster, and this is a straight section or tangent section, this is a curved section. I can find where the PC is, and where the PT is, where the PC is, where the PT is, and I can use, for instance, the Chord method to calculate what the radius of each section is. So that is the intuition. We can calculate, we can estimate the radius value. Now, for this specific purpose, I'm using modified Kmeans. So Kmeans is an iterative partitioning algorithm, and this objective is to minimize this sum of squared errors, the total sum of squared errors. So if you have K clusters, you would like to, this is the curvature value of the kth cluster is the average curvature value. So we're trying to find out the variance within cluster variance, and we want to minimize the SSE value. Now, the reason why it is called the modified K-means is because the standard clustering is unrestricted in space. In other words, the points in space are not given in an order, but in this case, in our case, is ordered, right? So for instance, in this one, I cannot take this point and put it in a cluster with a point from this one. So the clusters are clusters are contiguous. Okay, so that makes the clustering algorithm run a lot faster. Okay, so that is the reason why it's called the modified Kmeans. Now, instead of using curvature, we can use other explanatory variables. The reason why is because the one that I just showed you in Google Earth, it is done as good as, I mean, it was as good as it gets. I really tried my best, okay? But when you are doing all sorts of roadway links, it's not always perfect. There are inherent errors in the digitization while creating the GIS maps. So only relying on the curvature values might not yield reliable results. For instance, if you look at this curved line, where the blue line is the actual roadway, where the dots are the vertices that someone, the analyst, puts in to create the GIS maps. So you see that this vertex is out of line, right? So this, although it's a very small error, when you calculate the curvature, it kind of just creates all sorts of problem in the clustering algorithm. So this might just take this one as a cluster or this one as a cluster. So it the results go berserk because of this little mistake. So in order to remedy that, I can use other explanatory variables which can contribute to me trying to find out distinct roadway sections. So the ones that I use, so this, I kind of compiled all the variables that I saw in the literature that can give me an idea about if a roadway is a part of a tangent section or a curvature section. For instance, first we have the curvature. The second one is the bearing angle. The change in bearing angle, we have the distance between vertices, how close I tightly packed there together, the milepost, the radius at 3 consecutive vertices, radius of a circumscribed circle, changing cumulative angles, so on and so forth. And obviously they are all in different scales. So the entire, so I put all of these in one vector and I standardize them to make them in the same range. Okay, so Z is, in this case, is the standardized explanatory vector for any given vertex. So what are the caveats of this approach? The first thing, and it's the major thing, is okay, I can run this, but what is the optimal number of clusters? Where do I stop the clustering algorithm? Now, there are obviously many different approaches to find out the optimal number of clusters. You can use the elbow method. You can use the silhouette method, gap statistics. You have BIC approach, but all of these are based on the marginal reduction of the sum of squared errors. So unfortunately, all of those which are based on reduction of the SSE, they fail to detect the slight curves, meaning large radius and short section length. For instance, the one that I just very badly drew on the slide is, you can see a very slight curve. You can see perhaps the PC here and the PT here, and a very obvious curve with a small radius, and this is a large radius. Now, if imagine that these curves are a part of the same roadway, some way they are connected to each other. Now, if I go one more cluster, suppose that I created 10 clusters, and these two are part of those 10 clusters. If I go one more step, now the clustering algorithm that is based on the reduction of SST will have more benefit of dividing this obvious curve into two rather than dividing this to find out this small curve, right? So what do I do? That is why we came up with it's called a Patchup heuristic. What we do is, after we run the clustering algorithm, we calculate the radius of each section and determine whether it is a curved or tangent section based on the radius. If the radius is greater than 12,000 feet or some other reference point, we assume that it's a tangent section. Less, it's a curved section. Now, in the case of if we have contiguous curves, if each cluster, for instance, in the one that I have here, we have two clusters next to each, contiguous to each other, and they're all, both of them are obviously curved sections. So what is done in the algorithm, we run the clustering algorithm by setting a large value for k. So, and it terminates when the SSE does not change by increasing the number of clusters. Obviously, we have to we have to impose certain restrictions. For instance, the minimum cluster distance or the minimum number of clusters, minimum number of vertices in a cluster. Obviously, if you set the k value as large as possible, the final result will be each point itself, because that will be SSE will be 0. Now, after we run the algorithm, imposing restrictions, we have the clusters, and so when you look at these two clusters, obviously curved cluster, cluster K and cluster K plus 1, how do I determine that they are not two separate curvatures, or a compound curve, or a reverse curve? I mean, reverse curve is very easy. Obviously, their second derivatives are opposite of each other, the signs. But in this case, how do I find out that they are a part of the same curve? So in the Patchup heuristic, we find the center of the curve. We know the radius. We can find out the center. And the other one, we have the other center. Now, depending on how close they are to each other, the closer they are, the higher the probability that they are part of the same curve. So we check whether the distance between the centers are less than the minimum of the radius values times a sensitivity parameter alpha. So as the sensitivity parameter alpha is close to 0, we are more sensitive. So when you set it to 0.05, obviously you don't combine anything. Now if this rule, if this checkpoint is marked as yes, then we patch them into a single curve. And then you go through all the clusters like this, and then see if the clusters need to be patched together or not. And then you come up with the final number of clusters. So this is the approach of the cluster. This is the clustering approach. So now it comes to the validation of the results. We have completed the validation using many different data sets, but for this specific presentation, I picked an easier one because it's easier to follow. There are not many complex curves, so it is a good test bed to show the results of the approach. Excuse me. Okay, now the data is, the validation data is by the study of Xu and Wei from 2016. The curvature data is from, the alignment data is from Nevada. It is I-80, which is nearly 10.7 miles, and it's in the eastbound direction. The reason why this is, I'm using this roadway is because in this study, they meticulously reported the each curvature value, the start and end value, so it can be used by other researchers. So I downloaded the GIS shapefile of this roadway from the Nevada DOT website, and there are a total of 10 horizontal curves on this roadway, and the central angles they vary from nearly 16 to 49 degrees with an average of 25 degrees. And that, now, how do we compare, how do we evaluate the efficiency of any method, any horizontal alignment extraction method? Now for this one, we're using 5 different metrics. Now, in order to illustrate how they work, I have this hypothetical roadway alignment data. The blue ones are the actual horizontal alignment, where you see as with the solid lines, you have the curved sections. With the dashed lines, you have the tangent sections. There are 3 curved sections on this roadway and 2 tangent sections. And assume that I have, from some estimation algorithm, I have 4 curved sections and 2 tangent sections. How do I compare the efficiency of this estimated horizontal alignment data set? So the first one is the curve identification rate, and the second one is the tangent identification rate, meaning what is the percentage of curves that the algorithm can identify based on the actual horizontal alignment data. For instance, if there are, in this case, there are 3 actual curve sections, and this estimated one checks this one, checks this one. It is, I mean, this algorithm finds it, and it finds 3 out of 3. Although I found 4, but it checks all the curves. So, and 1 identification rate is 1. And as far as the tangent sections, there are 2 of them, and I spotted 2 of them, so it is 1. So this is the most common metric that metrics have been used in the literature to illustrate the efficiency of a curvature detection algorithm. Obviously, in this specific case, you can see that it does not always tell, it doesn't give the entire picture. Although we are identifying curves and tangents, we are here, I have an extra curved section, which in fact was not curved. So the M3 and M4 is the overlap ratio of curves and tangent sections. So it measures the ratio of overlap in length between curved and tangent sections, between actual and estimated alignment data. So in here, you can see that, so basically you take the length of the actual and the length of the estimated one, and then see how much of it kind of overlaps with the actual one. And then that gives you, this is M3 in this specific hypothetical example is 88.7% is identified. 88.7 of the curved sections was identified by the estimation, and similarly 70 or nearly 80% of the tangent sections were identified. And the last one, M5, is again borrowed from the literature. It shows the percentages of estimated curves with radii within 10, 25, and 50% of the actual radii. Now here, in this example, that means the 33% of the curves detected had a radius value that is less than 10% of the actual one. 66.7% of the curves had a radius value that is less than 25%. So it gives you an idea, it's a scale of how close you are to the actual radius values. Now, with that in mind, the results, obviously, I'm not going to go through them one by one. As I said before, there were 10 actual curve sections. So instead of going through one by one, I can use the matrix that I just presented and show you how well the algorithm works. All curves were identified, therefore, N1 curve identification ratio is 1. Now, 2 tangent sections out of 11, there were 11 tangent sections in the actual data, they were missed, and therefore it is only 82%. Now, the reason why we have M3 is 0.9, meaning 90%. The start and end points of curves do not actually match precisely. This is normal because this is a space discretization problem, right? So we have only a limited number of vertices that make up the entire roadway. So the overlap ratio is 90%, and the average undetected curve length is 210 feet. And the overlap ratio for the tangent sections is M4, which is 94%, and the average undetected tangent length is 196.8 feet. Now, as I said, this discrepancy is expected, because if you look at this, the vertex resolution, meaning the average distance between each between vertices on this specific roadway from the GIS map is 183 feet. So this scale of undetected length is expected. Now, this issue is not specific to GIS methods. There are studies that show that such discrepancies happen in many different methods, especially in the field measurements. If you do a field survey, from one field survey to another, there are differences in the PC and PT points and also the radius values. And looking at the M5, which shows us how close we are to the actual radii, the estimation of curve radius it depends on the correct detection of PC, meaning the start, and PT, the end of the curves, and also the vertex resolution, how close the vertices follow the roadway center line. Now we have 70% of the curves had radius values within 10% of the actual radius values, and 100% of the curves are within 25% of the actual radius. So this is a very good result, because let's face it, this is a freeway. So when you go from the freeway to the rural roadways, obviously these metrics start going down a little bit. Now, I guess I kind of rushed through the presentation. We are at the 40-minute mark, I believe. But now, as far as the future work, now, as I said, even though there are some inherent estimation errors, which are inevitable due to the space discretization of the continuous lines, and also the errors during the digitization process of the orthophotos to create GIS maps, the results are quite satisfactory. Now, as a matter of fact, as part of the research work that we did for New Jersey Department of Transportation, we created an online, easy to use web tool to process GIS centerline maps. It's called Curves. It is intended as an open access tool for interested researchers for their research work. And I believe I have a screenshot of the tool where you input the links and the node files, and then you create you select whether you want to do the entire network, or if you have a certain list of roadways that you would like to process. And depending on different parameters, you can adjust the sensitivity, you can adjust the radius threshold that determines whether a section is a curved section or a tangent section. And there are other things that I could not get into detail, but it shows on a map for each curved section, its center, and you can also download it in to Excel or a CSV file in a usable to a usable format. So this is still at a preliminary stage. We presented this work last month at the Transportation Research Board conference. The paper was accepted. So this is something that can be enhanced and given to researchers for their use, because we know that it is very hard to get the curvature data, especially for rural roadways, which is mandatory data for any safety analysis if anyone wants to use the highway safety manual. And the future work will focus on improving the this curves tool that we developed. So with that, I would like to end the presentation. I would like to thank you for listening. So if you have any questions, suggestions, or if you'd like to talk or send feedback, please shoot me an email. Thank you very much.
Okay, great. Bekir, thank you very much for talking about this research. like Bekir was saying, like Dr. Bartin was saying, please feel free to use the Q&A button at the bottom of the screen, and I'll read your questions out loud. In the meantime, I had a few of my own.
Sure.
So where in the process is the Curve software tool? You mentioned like it's going to be enhanced. What kind of enhancements are you thinking about?
The enhancements is so currently. Let me put this back on the share. Currently, John, if you look at the, let me go back 1 second. All right, so currently it requires users to put the link and the node files in a CSV format, which is very easy to do using any given GIS software tool. I mean, we use QGIS, which is an open, a free of charge GIS tool. It can be done by ArcMap as well, but it requires a manual input. I mean, you need to extract the link file and the node file and upload on the map. So what we would like to do is we would like to have the shape file imported directly, so the users do not have to worry about extracting the links and nodes files. The second one is currently the tool uses the chord method to find out the radius value. So we would like to use least squares methods. There are many methods available. It's a nonlinear kind of minimization. There are different methods like CASA method, the Tobin method. There are other geometric methods. So we would like to incorporate those into the program so users can select which ones they would like to utilize to estimate the radius values.
Okay, we have one question here. You can tell me if you need more information. Does your research consider, I think this is ramps and spirals?
By spiral, I believe Tang is talking about the spiral curves.
Yeah, Tang, you can speak up if we're getting this wrong. You can just type it again, but keep going.
I believe the ramps are not, okay. So let me start with the spiral. Spiral curves are using the vertices, using the discrete points in space. Spiral curves are almost impossible to detect. Okay, very hard thing to do. Okay, I believe there are papers that claim that they could, but I find it very hard to be true. The second, as far as the ramps, no, because ramps are quite easy. You can easily find out if you have the vertices of the ramps. You have to kind of make them, kind of isolate them, and then you can easily find out the ramps, which is, I didn't do it, we didn't do it, but it is quite possible to do.
Okay. At a high level, what kind of positive safety impacts are we looking at as a result of applying this research? So by better identifying curves, what kind of safety impact are we talking about?
Okay, now let me give you an example. For instance, when we were conducting the research project, so for two-lane, two-way rural roadways, if you would like to use highway safety manual, you need to find out the curve sections, okay? Now, we were relying on DOT because they said that there was some kind of a work done, an ongoing work that was done by a consulting company, that they were extracting the curvature data on rural roadways and using the survey vehicles that I mentioned. Then we couldn't wait, so so we did this. So for that work that they were doing, the field survey, the field vehicles, what they do is they find curve sections and to be able to put advisory speed limits. So you need that to be able to find the correct location to put the advisory warning signs. Because if you are approaching, so imagine if you're driving on a rural roadway and it is nighttime, you should be able to know that there's a curve coming up, right? So you need to know exactly where those curved sections are. So that is one of the aspects of, one of the advantages of knowing exactly where the curves are. The second is, as I said before, to be able to do some kind, any kind of predictive analysis on two-lane, two-way rural roadways, you need to have the curvature values to be able to use the highway safety manual functionalities.
Sure. So I don't know if I understood your metrics and evaluation section correctly, but from what I understood, the overestimating the number of curves is common, or the amount of curve section, or was that just the example you gave? So you picked up your algorithm picked up 4 sections of curve.
No, that was a hypothetical thing. That was a hypothetical.
Okay, got it.
Okay. Hey Hong, how are you? I see your question here. Okay. So let me see. Is the radius calculated based on the deflection of the first and the last vertex of the curve? No, the radius, Hong, is so if when I find a cluster, right? So I know exactly the first point, first vertex of the curve, and the last vertex of the curve. So I use the chord method. So I can find out the chord length. I can find out the middle ordinates. It requires some kind of a programming, but that gives me the radius. So it's based on the location of the PC and the PT. If I don't know if that answers your question, but if not, you can type back. The resolution of the vertex, absolutely, it impacts the results, depending on the curve characteristics, right? So if the curve is a sharp curve and you're using 50 feet instead of 20 feet, obviously it impacts the results. And also the resolution impacts the location of the PC and the PT, right? So if instead of using 50, if you're using 20 feet of resolution, your PC or PT will be much more reliable, and therefore your radius will be more reliable. So that impacts. The third question is the S curves. You mean the reverse curves, I believe. How can you obtain the S curves or complicated one? Me obtain or detect? I believe you mean the detect. It detects the S curves because when you, so I use the curvature value, right? Curvature value among other explanatory variables. So the curvature value will be different. So the second order derivative will have a negative value or positive value. So it can identify the S curves. But the complicated ones, as Tang asked, the spiral curves, no, it cannot be. So by the way, we have detected all the rural roadways in New Jersey, the two-lane, two-way, using this algorithm, and runs in about 10 minutes and puts everything in a usable format.
Okay, I think Tang just mentioned a paper, I think some work that their group has done. I'm going to enter the title and the paper.
Yeah, I see it right here. Yeah, this is with with Eric, right? Eric Green. Yeah, I remember the name. This is using the GPS. I believe I remember this paper. It uses the GPS data instead of the GIS data. I'll have a look at it more carefully. Thank you very much, Tang.
Okay.
By the way, if you have any questions, anything that you will, any feedback, I will appreciate it.
Okay, and then Hong just has a comment that developed the statewide curve data and tool for VDOT, and it looks like the agencies are very interested in knowing different types of curves, simple curves, S-shaped curves, etc.
Yeah, the simple curves are quite simple. I mean, as the name implies, it's quite simple and easy to detect. I mean, depending on the central angle and the radius, but as I said, the S curve is okay, but the spiral, data. Spiral and compound is depending on the sensitivity that you use, it can be done. But again, this is just using the GIS. If you have any kind of GPS data with closer packed vertices, the results will be much more reliable. There could be other ways of obtaining these data, which we are working on. So we're not only relying on the GIS data, we can get that from other means.
Okay, I think I want to ask one more question and then we'll start to wrap up here. So just to bounce off of my previous question, in doing this research, have you, I don't know much about safety work in transportation, but by better identifying curves, you mentioned for nighttime driving or reduced speed, was there any reference in the literature at like a potential impact, like a safety impact? What, I don't know, like reduced number of incidents if we're better able to, identify these curves?
Yeah, that is exactly what I was referring to in the highway safety manual. That the reason why the alignment data, or to be specific, the radius and the curve length is required, is because you would like to find out what the crash modification factor related to curves are. Meaning, for instance, if the predictive function gives you, for instance, X number of crashes per year for a tangent section, what happens if that section is not tangent but is a curved section with a certain radius and length, right? So obviously the experience and the intuition tells us that there will be more number of crashes, correct? So the crash modification factor gives you that factor, how much it will increase. So you would like to find out what is the crash modification factor for each curved section, and for that you need to know what the R is, meaning the radius, and the curve length is. So that's why we need to be able to locate exactly where the curves are and find their radius and length values.
Very cool. Okay, Bekir, thank you so much. And just some ending notes here. If you enjoyed this webinar, definitely follow C2 Smart on Twitter, join our LinkedIn group and our mailing list. We're excited to have several webinars in the works for the coming months. Thank you again, Bekir, Dr. Bartin, and thank you to everyone who tuned into this webinar.
Okay. Thank you, guys.